Hi everyone, welcome to my channel. In this lesson I would like to introduce an educational package dedicated to the implementation of fully pipelined um, Direct Digital Synthesizer using Vitis high-level synthesis. The package includes design steps, optimization techniques, and guidance on integration of the DDS IP core into Think 7000 platform, namely RTZ720 that I'm using, for efficient signal processing. I would like to start with the hardware design from the educational package. The hardware design includes processing system or Think 7000 and programmable logic. In programmable logic, there are three DDS IP core implementations, so namely straightforward implementation with a truncated phase and two more implementation in order to improve spurious-free dynamic range. So there are DDS with phase dithering and DDS with correction of the output by using Taylor series. The data transfer between IP cores and DDR memory are organized by using access stream switches that are connected to Xilinx XCDMA IP core. So all this programmable logic operates under Linux, running on Cortex ARM A9 2-core processor. So therefore, educational package includes development of fully pipelining DDS IP core in Vitis high-level synthesis. Three implementation of DDS, it's truncated, dithering phase, and Taylor series output corrected. Integration and real-time configuration of the Xilinx XCDMA IP core and access switches IP cores under Linux. Then DDS IP core spurious-free dynamic range estimation by using Python script. And since, as I mentioned already, this system is running under Linux, so Linux deployment for Think 7000, namely for RTZ720 board, also provided. So, if you would like to get the sources, I will describe structure of the sources. Feel free to connect me, and I will explain how to make donation and obtain all these sources. So, this structure of the sources, the package includes the following sources. First of all, it's a build root out of three configurations that allows you to deploy Linux with high-level synthesis IP core support. Vitis tickle scripts for automating such projects like Vitis high-level synthesis project, Vivada hardware design project, and creation of bootloader for CD card deployment. Vitis high-level synthesis C++ sources for all IP cores and programmable logic. Python script for spurious-free dynamic range estimation and for parsing outputs from the high-level synthesis DDS implementation IP core. And also Linux C application where I demonstrate how to handle Xilinx IP cores on the Linux, how to organize transfer between DDS IP core, and as a bonus here, it's implementation of phase generator for all IP cores. So phase generator allows to create a signal like, for example, singleton, linear signal with linear frequency modulation, and phase shift key modulation, for example, or other kind of signals. So in order to leverage the package, the following requirements should be met. So as setup, I'm using RTZ720 board from Digiland, but again, another board also can be used. So the board is connected via SSH to the host, host running Ubuntu 20.4 with installed Vitis on it. So therefore, all packages, all mandatory packages required for build-up Vitis also are needed. Okay, let's turn to Vitis high-level synthesis DDS IP core implementation. So here the architecture of the IP core, where I have access stream interface, so as input and as output, and a set of different sub-functions. So namely sub-functions, it's for reading, for writing access, phase dithering with implemented random number generator, quantizer, lookup table, since the DDS IP core is based on lookup table method, and algorithm for Taylor series correction. The access stream interface, so input access stream, it's 32 bits for phase, where the phase as a flat data type can be provided. And as output, it's a 64 bits, 32 bits per either imaginary or for real type. Let's take a look on synthesis and implementation report for 8192 input sample space. So here can be seen that initiation interval of one clock cycle ensures fully pipelined implementation of entire IP core for all three variants. So besides that, iteration latency also can be estimated based on sum of iteration latency for all subfunctions and resources. So for resources, let's consider implementation report. I summarized everything in one common plot. So for truncated implementation, so truncated, data, and corrected implementation. So DSP blocks for truncated implementation, since it's a straightforward implementation, there is no need to have any DSP blocks. Deterrent implementation requires at least 8 DSP blocks, so mostly for implementation of a random number generator in phase different subfunction. And 10 DSP blocks for corrected implementation of the DDS IP core because of the computation, additional computation required in Taylor series correction subfunction. The same amount of BRAMs for all three variants, and the latency. So latency here values demonstrates how long, how many clock cycles it takes after the first sample was input sample provided, and so until the first output sample. So the truncated implementation requires the less amount of clock cycles, and yeah, so as can be seen here, corrected with Taylor series also required not so many clock cycles, unlike, for example, implementation with a deterred phase. But again, because of a random number generator that takes time in order to generate a noise for phase deterrent algorithm. Let's turn to the test procedure in order to estimate functionality of the IP core. So here, the Vivada block design with integrated DDS high-level synthesis IP cores that I'm using in the package. So the Vivada block design includes 3 IP cores connected, as I mentioned already, to AXI stream switches, and AXI stream switches are connected to AXI DMA. So the procedure flow is quite simple. First, it compiles the application on the host. Afterwards, copy compiled application on the target where this application can be executed, and therefore 3 binary files corresponding to output of the each output of the each IP core will be created. Besides that, performance timing by using timings can be also estimated here. And afterwards, these 3 output files needs to be copied back to the host, and by using Python script, spurious free dynamic range can be estimated. So this is a spurious free dynamic range estimation for one of the tests that I conducted before. What can be seen from this plot? So truncated output, DDS truncated output has this regularity with the spurs related to phase truncation, and therefore it provides spurious free dynamic range equal to -72 dB. By phase deterrence, or by adding a small noise to the phase before truncating, so spurious free dynamic range becomes minus 90 decibel, and so with correction output by using Taylor series, spurious free dynamic range reaches -100 dB, so that is quite good. Right now I will demonstrate how to run the test procedure. Okay, so here are my dear folder of the repository. First of all, I would like to go to the folder with C application, and let's compile the application. Okay, so I have compiled the application, then I have connected the board. Let's try to ping one. Yeah, okay, I am able to ping. So let's try to connect via SSH. Then, yeah. Okay, so yeah, here we are. Here I have two folders. I already create folder with DDS. And yeah, all I need is to create, it's to copy. First, let's copy a compiled application to the target. It's CP DDS test. DDS. Okay, let's go to the target and let's check. Okay, here are the application. Let's run the application. DDS test. Yeah, it gives output. Okay, it gives output. It's a timing, so IP core. So basically, the time is the same because the difference is not so. The difference is not so basically so distribution between all three IP cores quite fast it works. Okay, and let's take a look. So here there are three binary files that corresponds to the output of each IP core. Let's copy this file back to the host. So to do this cp and DDS d out yeah, and so sorry, first of all I have to create a folder, and so I have to go one step back here and make a dir sim folder. Then let's copy in the sim folder all binary files. This the out in the sim folder. Okay, three files is here, so and therefore, since we have three files here, I can run Python script for spurious free dynamic range estimation Python folder and DDS. Okay, without anything, just like this is okay. It's okay, yeah, and here is the figure. So here is the plot. Um, so three outputs and the difference. DDS corrected output gives so truncate minus 72 dB, deterrent 86 and 88, not very big difference, but for Taylor series corrected output. Let's change a signal in C application and run one more time. So I need to go back to CD DDS. So let's make clean and let's do some changes. DDS output user. Okay, so for example, start frequency I use only one here. You can say let me change here, for example, for 3.3, like this, for example. Okay, make. Okay, the application is here. Let's copy it to the target. SCP. Okay, go up. Let's go to the target here and let's call again. Okay, yeah, it works. Okay, three binary files that we need to copy again back to the host. Okay, three binary files is here, so therefore we can call the Python script, and let's take a look on spurious free dynamic range one more time. So now right now the situation's a little bit better. So currently spurious free is still the same for truncated output, minus 72, minus 91 for IP core with deterrent phase, and minus 95 for IP core with output corrected by Taylor series. Okay, so I hope the lesson, this workshop was quite useful. So I wish you good luck with your embedded design. And if you would like to boost your experience, please feel free to connect me in order to obtain all sources of this educational package.